So, what I was saying is that basically the fluctuation dynamo, the question is whether you can grow the field on.
Maybe one comment.
Yeah.
That the 3.5 earlier simulations with full DNS also saw, we also saw that
3.5, no?
So it's kind of consistent with what you're saying with finite time.
Yes, except for the fact that, yeah, that's right, except for the fact that the Kazantsev result is for a single scale flow and for scales which are smaller than the scale of the flow. Usually you see with DNS, even with turbulent flows and all that. So we are also puzzled. But yeah, I will show you the 3.5 we keep seeing all the time. I don't think there is a nice qualitative explanation which I know of for the 3.5. Right.
Can I ask one more question?
Yes, yes, absolutely.
About this flat freezing and random stretching.
Yes.
Is random you mean Gaussian?
Not necessarily random. In fact, it need not even be turbulent. It can just be random in the sense that something which is kind of has a probabilistic interpretation way of this thing, that you don't, like the difference will be, for example, suppose I have shear in just one direction, which will happen in the galaxy. The galaxy will simply wind up the field, shear it all the time. The growth in that thing, the field will also grow even there, but the growth will be linear in time depending upon the shear rate. Whereas because this thing is random, it just stretches for some time. It may be a small growth, but then it stretches in different direction again, and then it random walks in this thing, and then it doesn't turn out to be linear anymore. It's now exponential, because it acts on the previous field to stretch it in some other way. And so that's the interesting good thing about the random stretching. So the random stretching, flux freezing led to growth of A, B, but now whether it actually grows depended upon this quantitative question. And what Kazantsev showed was that as long as your magnetic Reynolds number is beyond a critical value, you will grow the field. Now actually there are two things which are preventing the field growth, and I forgot to mention one of them. One is of course resistance, because field is going into smaller and smaller scales. But very importantly, there is something which I think I have first seen emphasized in this context by Eink, is just cancellation, which is well known to the standard dynamo people, that basically if you are looking at one point in space and you look at the fluid elements backward in time, then the field at this point in space at some particular time is being advected by points, various places in the past. From very distant points, the field is being brought to this point here. So when it's being brought from very uncorrelated regions, the field will automatically not reinforce itself. So there will be a large effect of cancellation. So this will bring the fields of opposite kind of directions to any particular place. And then of course resistance is what is required to kill the field actually. To what extent this affects and what extent this affects is something which I do not know the answer to at present. But the basic message is, provided you have magnetic Reynolds number more than some very modest value, you will have a fast growth on some, the time scale will be 10 to the 7 years for galaxies, 10 to the 8 years for galaxy clusters. Field will become intermittent. And the whole question is, how does it saturate? There is no problem in a turbulent system of getting magnetic energy growth in the context of galaxy and cluster plasma. And how it saturates is important for all these things about Faraday rotation that we are talking about, the young galaxy Faraday rotation, the cluster Faraday rotation, and also will have a bearing on what I'll talk about later on mean field dynamos. Okay, we went through these two things. So to really go into something to do with saturation, you can either build simple models or you have to do a simulation. Let me first show you the results of one such simulation. This one is by Pallavi in a long time back, okay, 2012. And, and it had, of course, assumed Prandtl number 1. Now, whenever you are doing a numerical simulation, it's extremely difficult to go away from 1 unit Prandtl number. You can go to maybe 10 and 0.1, because if you are trying to resolve the resistive scale, and you are trying to resolve the viscous dissipation scale, okay, then you want to put as much of your effort into having big scales in the problem plus these dissipation scales in the problem. If both the dissipation scales are different and you want to resolve both of them, then it automatically means you are in some kind of problem. So no simulation really moves too much away from 1 in terms of Prandtl number, maybe to something like 0.1. These are all of course magnetic Prandtl number. Either 0.1 to 10 would be the kind of range. If they really move to, let's say, 100 and all that, and people have done that, then they are not completely resolving the dissipative scales, because the kind of simulation that one does. Here one can see that basically the field has started from a weak stage where this is the magnetic power spectrum plotted as a function of the wave number k. So large k means small scales, length scales, and this is the box scale. In this is a simulation of a dynamo in a periodic box, the periodic boundary condition. The flow is driven basically between k of 1 and 2, which means almost on the scale of the box, it's a random flow which is driven. The forcing is almost delta correlated in time. The velocity field is not delta correlated because of the fact that there's inertia to the fluid. It will automatically have a correlation time which will be at least as long as the smallest eddy turnover time that you have in the problem. So it's a more realistic velocity field. It doesn't have those Kazantsev restrictions. And one, as Mahendra was telling me just now, one still sees a k to the 3/2 spectrum initially, and he also has seen it in their direct simulations. The question is, does it remain like this as it grows? In which case all the power will be on large k, and you may not get enough Faraday rotation from such a box to explain observations. But what it does do is, it turns out that it orders itself. When Lorentz forces become important, this part comes and hits some kind of barrier, then the peak kind of keeps shifting, and the final saturated state of the field is this. This is the velocity spectrum, that's the magnetic spectrum. It is much more ordered than initial, and we have quantified this. For example, in this particular simulation, the integral scale, which is defined as some average of 1 over k over the whole spectrum, 2 pi over k over the whole spectrum, increased by about a factor of 3 or so. This is fairly modest, but it did increase, and it in fact increases when the Lorentz forces become important. So this is how this field actually looks. There is one component of the field, the z component, in the 3 faces in the box, and yellow is strongly positive and blue is strongly negative. These are all measured in terms of the RMS field, and you can see the kind of intermittent field that you have. This is not the field that you would want to see in a galaxy, of course, but it could be the field that you would want to see in a cluster, which is all random fields, provided it can explain the amount of Faraday rotation that you have. Now, this is simulation. There has also been some amount of analytic, not work, I would say analytic guesses of how the whole dynamo would saturate, how this fluctuation dynamo saturates. I have tried to spend some time on it now long back, 10 years, 12 years back, dozen years back at least, on 2 papers which you can look at, building some toy models of nonlinear saturation of these dynamos. And in those papers what I show is that the dynamo saturates by driving the magnetic Reynolds number. Because of the nonlinear effects, it gets driven to some kind of the critical Reynolds number for dynamo growth. Basically the diffusion kind of gets renormalized by addition of some magnetic field there, okay? And then you will find that the resistive scale has actually increased, or some scale, coherent scale has increased from Rm to the half here to L by R crit to the half. Unfortunately, Alex is not here, okay, because he and his collaborators have argued that the dynamo saturates due to reduced stretching, but the coherent scale of the field remains the resistive scale, which is extremely small. But their results are more or less limited to very high Prandtl number simulations. Okay? here it did not depend upon that. So you can see that there is absolutely divergent view on this, okay, and it's not clear who will be right or who will be wrong. Maybe both are right in different contexts of high PM versus PM equal to 1 or different this thing. But so that's why it is absolutely essential that you do some other thing than just do all these analytic calculations, because you should remember that this is a kind of a closure problem, and any such closure problem you have to make an approximation when you are dealing with a nonlinear closure problem. One person's favorite closure will be another person's poison, okay, and you will never agree really unless you compare with something else. So for okay, I should also show that there are the highest resolution simulation that one has at present of these fluctuation dynamos. There is a spectrum at the saturated state for PM equal to 1, and here clearly it is not peaked at resistive scales. You can see that there is a drop off of something like the magnetic, this is the dotted curve is the magnetic power spectrum. It kind of drops off like almost like k to the 3/2, okay. This is the total power, of course, drops off as k to the 3/2. This also drops off from the forcing to the dissipative scale. So here it's not peaked like this, how it was in the Kazantsev stage. The nonlinear back reaction, the Lorentz force, has ordered the field. This is a simulation by Niels Hogan, Axel and Dobler, and a similar result also holds in another high resolution simulation by Eink et al., which was published in Nature. And in fact, you can go and get all the data from this. They have put it public in the Johns Hopkins University database. You can get it if you can have your internet connectivity working continuously. And when we tried to get it, or Pallavi was trying to get it, it was impossible. You will always break somewhere. So again, you can see that the magnetic power spectrum, which is now this blue line, okay, W is this blue here, is again dropping with K. So although the kinematic prediction for the fluctuation dynamo is a K to the 3/2 spectrum which increases with K, the nonlinear back reaction, at least for PM equal to 1, has made it go down with K. Okay. Now so these are of course PM equal to 1. So we also try to, one more thing which I thought it should be worth mentioning. I already told you that cluster plasma is not very well approximated by MHD because of the very long mean free paths. So what would plasma effects do to this fluctuation dynamo? This is of course beyond the scope of the present school, nor is it something which I understand very well, but there has been one such simulation by these people, Santos, Lima and all, published. This is the result that they got for collisional MHD, as they call it. Now what the plasma effects do is to create pressure anisotropy. I mean, what the evolving magnetic field does, because suppose you take magnetic field and squeeze it somewhere, increase its strength somewhere. There are adiabatic invariants in a plasma. For example, the perpendicular momentum, this thing is momentum, yes, adiabatic is invariant. Okay? So your pressure will become anisotropic, that is, pressure will increase in the perpendicular directions compared to parallel directions. No plasma likes such things. They all want to be eventually Maxwellian. This leads to instabilities. These instabilities generate small scale fluctuations. Those small scale fluctuations will try to restore the isotropy of the pressure. And you can ask, what do those small scale fluctuations do to viscosity? What do those small scale fluctuations do to resistivity? Viscosity is something which Alex has worked on quite a lot, and these people try to implement some of those ideas. And then if those pressure anisotropy remains always, then you don't get a dynamo at all. The dynamo becomes highly inefficient. If the pressure anisotropy can always be restored to some marginal value for instability, there seems to be no difference, that is this case, there seems to be no difference between the collisionless MHD and collisional MHD. So of course, pragmatic people, and astronomers are fairly pragmatic, kind of take the viewpoint that, okay, anything which I don't know, I don't worry about. Okay. And in fact, it will be pushed to some extreme because there will be huge number of astronomers who will not worry about magnetic field, which you will be at least worrying about. Okay. So, in a pragmatic view, you can just say that, okay, there are all these collision-less effects which will all maybe increase the collisionality of the plasma and make MHD work at some level. Okay. That's the message you could take home from this. So, to address this question of whether you have coherent fields sufficiently coherent for explaining Faraday rotation, what we decided to do, and whenever I say we decided to do, it's mostly Pallavi. I'll just be doing the deciding and she'll be doing the work and the results, is to shoot lines of sight, okay, through a box of this field and just directly measure the Faraday rotation. Now, whenever you measure something, you have to compare it with something which allows you to say how good this measurement is. So, suppose you imagine that each turbulent cell has an ordered field, and then from one turbulent cell to another turbulent cell, the field randomly changes. The amount of Faraday rotation that you expect is given by this expression. There is a random walk, that's why you get a square root of L is the capital L is the length of the box, small l is the length of the forcing eddies, and BRMS is the RMS field, and E is the density in the plasma, root 3 because you are only sensitive to one component in Faraday rotation. Now, if you normalize by this amount and just shoot lines of sight and directly measure the Faraday rotation through one of these boxes, it turns out by the end of the simulation where you saturate the field, you get about 40% of what you would have expected in this ideal case. So, even though the field looks highly intermittent, okay, that it's changing all over the place, it's concentrated in very small regions, you do get significant Faraday rotation from such a thing. We also try to test, suppose you remove high field regions which are greater than twice the RMS or greater than 1 times the RMS, what Faraday rotation will remain? It turns out you don't lose too much if you remove the high field regions of greater than 2 RMS times the field. So, you could ask, is the Faraday rotation being produced in the places where the field is strong, or is it being produced in the general sea of mess that you have? And the picture seems to be that it's being produced in the general sea that you have, which is very interesting because you could imagine people always, when they show you pretty pictures, they show you things where things are strong. They show you where field is strong, they show you volumes where something else is strong. But the general place where the field may be weaker, or it is at least just the RMS value, could be behaving very differently from where fields are all very strong. And that seems to be the case here, that it looks as if the field is not that incoherent in the whole volume, whereas when you see such a picture of a box which has 1 BRMS, 2, 3 BRMS, it seems to be concentrated only in small structures. Most of the red region where you think the field is weak may be producing most of the Faraday rotation that we see, and that we have just demonstrated by directly measuring the whole thing. So, so it seems to be partially good news, but as I said, the integral scale in this simulation in the best case only increased by a factor of 3. So, it's very far from trying to start from some resistive scale in a real plasma to the forcing scale that you are driving the motions at. And this is something which we will keep in mind all the time, and we will keep looking at this issue. Now, I want to switch tracks slightly. What happens is when this flow has helicity. So far we just said there's a random flow, and we described the random flow with some kind of correlation functions, this TL, Tn and TL. Now suppose you add a helical piece to that correlation function. This problem was also tackled quite a long time back by Weinstein and Kichatinov in, that may be 86, not 96, 86. Since then various people have re-derived this set of equations. You can generalize the Kazantsev equation to this thing with helicity. And in fact, this is Rokchevsky and Clearin. This is my paper in '99, and this is Kim and Hughes, David Hughes, will be here next week. All of us have re-derived these equations. Now it's cast in the same form that I had for the longitudinal correlation function. The Kazantsev had only up to this piece here. Okay? But probably this interpretation is more started in my paper here. So there is this diffusion term, there is the growth term. The presence of a helical piece to the velocity introduces a coupling to a helical piece in the magnetic field. So the magnetic correlator also has a helical piece, yes. Good question. Helicity, helical motions firstly are screw-like motions. So you have vorticity, which is omega or zeta, which Chris Jones defined, which is curl of V. Helicity is V dot curl of V and taken an average over this whole fluid or something. So it's like if you have rotational vertical motion, but it's also going in some direction. So you have like a helix, right? So the motion is helical. So if it's going in one way, it is maybe whatever, right-handed, left-handed screw motion. If it's going the other way, it's the other. So if you have a rotation like this and coming towards you, you'll have one sign of helicity. If it's going away from you, you'll have a different sign of helicity. Now, interestingly, if you take a screw, whether you screw it or unscrew it, it has the same helicity. Because the handedness of the screw is already determined. When you screw it in, you're rotating in one direction and you're going towards you, let's say. So it has one sign. When you're unscrewing it, you're rotating in opposite direction and going away. So V dot curl V turns out to have the same sign. So that is helicity.
What if the radius of the circle, corresponding circle also is changing, either it is expanding or
Oh, more complicated.
attenuated and so on. There are other curves to
No. Yes.
So you said you found the RM critical value for this model.
Right.
Can you use a particular form for Tn and Tl?
Yeah. Then only you can get a critical RM. So for example, you can use anything that you want, you'll get in that range, provided you have one length scale which is defining that RM. Okay.
So you used
So for example, you can just use an exponential cutting off, e to the minus r by L for TL.
so that means you are in the viscous regime.
Yes. You can also simulate the turbulent regime by putting power laws before having these exponential cutoffs. Then it's determined by whether the RM is greater than R critical for the viscous scale. If it's not, you will come in between and you can have great amount of fun with this Kazantsev equation. You can put various models for TL which simulate small Prandtl number, large Prandtl number, various different power spectrum, Kolmogorov spectrum, shock spectrum, and there have been people who have been playing around with this.
What if we have a dual spectrum? What do you
Dual spectrum, two scales. Oh,
scaling laws?
no, I've never tried that. But what will happen basically, firstly you will have to ask whether both scales have RM greater than R critical. Then you have to ask which scale has the smaller turnover time, eddy turnover time. And that will grow first. But there will be a reflection of the other scale also in the correlation function, but it will be dominated by that scale which is fastest growing. Whenever you have exponential growths of various things, the thing which grows fastest will dominate in the kinematic regime.
Can I ask, is there ever an objection that this Kazantsev model has infinite kinetic energy?
Yeah. No.
And therefore it seems difficult to really handle.
It's not difficult to handle mathematically, you mean.
Well, yeah, I mean, you can't even. How can you
Energy
define-
dense, our universe has infinite energy, but the energy density is finite.
Well, okay, I have no idea. What's the domain in which you're working?
It is infinite.
Infinite domain.
Yeah, infinite.
But anyway, I mean,
But the correlation scale is not infinity.
no, but it's just the presence of that delta function that worries me. It's
Absolutely. That delta function in time is what has worried all of us, and we have tried to get away from it. Like the paper which I was referring to, we have tried to look at what are called renewing flows,
Okay.
which kind of last for some time and then renew itself. And then we can try to write down everything, but we are not able to yet. It becomes, the whole evolution becomes non-local in space, not a differential equation like this. But in the lowest order in this correlation time, we kept up to first order, then it becomes a differential equation which we have solved and then try to show, and we have some results on that. We are all worried about the same problem. That's why one does also numerical simulation which doesn't have this problem. But many of the results of Kazantsev, the beauty of the Kazantsev problem is that before that there was Bierman, there was also Batchelor, thanks. There was Batchelor and there was Kreiknen and Nagarajan, who were all trying to argue if there will be a dynamo or not dynamo, no dynamo. And they didn't get anywhere basically because all the time scales are the same. The dissipation and growth time scales are the same. Kazantsev thing is, as far as I know, the first demonstration that without helicity, without any of these things, just a random flow will grow the magnetic field above a modest magnetic Reynolds number. And it was not really appreciated in the West for a very long time. And it was brought, of course, and of course, huge amount of development has since taken place because it's a mathematically fantastic, rich field. Okay, you can work out intermittency. There's that various things you can do in this.
Maybe I missed this. What is the magnetic Reynolds number, the critical?
30 to 100, depending on what TL you choose. So, yeah, I had that in this slide. Yeah. Oh, I had it. Yep, 30 to. Yeah. Now, if you go and do your numerical simulation and PM equal to 1, let's say, and you're forcing on some scale, it turns out that the critical Reynolds number is also about 35, but defined differently, maybe about 100, same. It is not very different. So, but the simulation is limited by how much Reynolds number that you can achieve. The model is not limited by that. That's why you have interesting things. And there is also nice insight. I mean, you have mapped to a potential problem.
I'll just make some comments. So actually the critical element, R critical depends quite sensitively on the initial condition, for example.
It doesn't.
No, well, not in this model, but in simulations and experiments. Experiments doesn't matter because there is a...
No, as far as random initial conditions go, if it depended on initial condition, you are in trouble.
Yeah, no, it depends on initial condition. The dynamo transition or any other transition.
But you know, Mahendra, the simple thing which I would say is that we are so far above the critical value. This transition is never important in astrophysics.
That's true.
Okay.
So R critical.
Of course, you can say, I have no problem if you put 2 pi there, 2 pi squared there, but there is an R critical which is determinable for a given correlation function. That's all I'm saying.
Yeah. But this will be universal or not? It's not. It won't be universal.
No, nothing will be universal in this way. What is universal is the fact that, this, for example, seems to be a very robust result, the k to the 3/2, for example, seems to be a very robust result. That there is dynamo seems to be a robust result. Of course, you could easily go into just simulations and do everything, but you know as well that how much will you do? Right.
One more thing which for problem number 1 at least, let me just make this comment, that we are very sure that the growth, problem number 1, if you force the large scale U, then large scale B grows fastest. Rather, that's a dominant growth, large scale B. So the most energy transfer takes place from U large to B large.
Yeah, but you
That's
know,
why we did this one. So it is not necessarily that all the growth happens at the small scale. For problem number 1, I won't believe. Problem number 20, we saw that. But problem number 1 is.
but what spectrum? You got the same spectrum, no? Finally.
No, actually we grow this. So it depends on this. Problem number 1, energy, if you put the seed field at small k, then it go from large U, small k U to small k B.
That is always there, but won't you, didn't you have small ku to large kb?
Yeah, that is the PM20.
No, even for PM1.
PM1.
Otherwise, you will never get this, no? See, you will never get this. You must have it, I am sure.
Well, PM1 we didn't do the dynamo simulation. PM1 we didn't do it, but we are basically looking at the transfers.
No, but if you did the dynamo simulation PM1, you will have this. I mean, that's what everybody has got always, that the power is peaked on small scales.
PM.02, for point 2 we did this small scale dynamo, small PM dynamo.
Right.
It wasn't, well, 3.5 is there too, but the growth.
Yeah, I will show you if I have time PM.1 also, which we have done recently. Correct. Okay, so let me move because it's now time to move. Okay, if you have helicity and you map it into the same Kazantsev problem, something fantastically interesting happens. Now, instead of an equation for just ML, you have to also have an equation for the helical part of the magnetic correlator. Okay, so you get two equations. You would have got three equations, but divergence B is 0, that relates two of the functions. Okay. Now, in these two equations, the helicity also can grow, but suppose you look at large r, at r larger than the correlation scale of the flow, then all these terms drop out. I mean, this eta t, which had this turbulent diffusion, it just becomes purely turbulent diffusion. The g kind of had derivatives of TL, which drops to 0. This term also has pure turbulent diffusion, but these two terms don't go to 0. This alpha, suppose you have a 0, if your helicity, your net helicity in the system, then this coefficient, which I have called alpha for a specific purpose, doesn't go to 0. What it basically means, at large distances, large separations, x minus y being large, you have a growth of both exponential growth of something on large scales, although you are stirring everything on small scales. So this is the first indication that helicity does something qualitatively different. Of course, various people are going to say it in different ways. I am saying it in this way basically because it's a very nice intuitive way from the Kazantsev problem. In fact, if you go to a quasi-steady state, ML dot equal to 0, H dot equal to 0, the same Kazantsev equation now becomes a 0 for 0 eigenvalue, like Schrodinger type equation, but with a modified potential. And if you look at what that modified potential is, if you have helicity, this is the potential well, if you have bound states, you have growing modes. Once you introduce a non-zero helicity, this potential dips back again, depends upon the amount of helicity you have, and it allows for tunneling of these bound states to larger scale correlations. So you can look at small scale dynamo as a bound state problem. What I'm heading towards is looking at the large scale dynamo as a tunneling problem. You are stirring in some small scale, and suddenly you are finding correlations on a bigger scale. In the Kazantsev picture, this process corresponds to like quantum mechanical tunneling that you have. There's no, of course, uncertainty anywhere. It's just the equations have the same form. It's as if you started with something which is bound somewhere, and suddenly you find a probability for it to be somewhere far away. Okay? Of course, this is not how you would want to, I mean, it will take some time to go into this, so I'll just wanted to mention this. I have just drawn it, that's my sketch. Yeah, there will be a scale separation. No. Even in tunneling, you get exponential dying thing, no? Wave function. Wave function is not 0 in between, right? Yeah. So how much power you will get from this, how much large scale power you will get from a small scale bound state, depends upon that scale separation. So which one is the boss and who is the slave? And I'll come back to this a bit later. Now, if you just do directly numerical simulations, for example, this is again a set of periodic box simulations with helicity, and it's not a very high magnetic Reynolds number simulation. and I'm just using it to illustrate the fact that you get the large scale field. These are simulations done by Axel from 2001 to today. And in this particular simulation, the fluid has been forced at a very small scale, at a wave number of 15 in this case. Okay? And what you see is that initially there's this random field, okay? And finally the field is ordered on the whole scale of the box. So the field has coherent scale has increased by this factor of 15. This only happens if you have helicity. So this is if you want a simulation, but then the simulation is limited because the Reynolds number is pretty small, and in fact it's limited by something else which I'll come to hopefully, by helicity conservation, which is an important thing here. Of course, neither of these ways is the standard way in which people talk about large scale dynamos. I was hoping somebody will do this. So anyway, I had put down some stuff. Suppose you want to describe large scale fields, the generation of large scale fields on scales bigger than that of the stirring scale. So you typically want to do the following thing. You have the induction equation. You have some velocity field which is stirring the fluid on some small scale. And you want to ask what are the things which are on much bigger scales. So you typically will start with the velocity field, break it up into a mean flow and a fluctuating flow, small u and u bar. The magnetic field into a mean plus a fluctuation, small b is the fluctuation, b bar is. So to define these bars, you have to do some kind of averaging. The averaging that you would like to do should obey what are called Reynolds rules. Otherwise you won't make any progress. The averaging has to be such that when you add two quantities and average, it's the same as addition of the averages. Or if you average and average, it should remain the same. Now, it's not obvious that this will always happen. For example, imagine doing Gaussian smoothing to average something. You smooth something and you get some average. Now you convolve it again by another Gaussian, the same Gaussian. Now the Gaussian width has increased. So you will not get the same thing. So Gaussian smoothing doesn't obey Reynolds rules, all the Reynolds rules. But for example, if you have a periodic box and you do horizontal averaging, or you average on one direction, or in the context of the sun, you average along what are they? Latitudes. Okay? So you define an axisymmetric mean field. Those averages do obey Reynolds rules. So you should be careful about what averages obey and what do not. And in fact, there's a nice way of formulating everything, which I discovered from IISc, of doing things independent of this kind of averaging. Okay? And there's a nice way of formulating things like that. So you have to satisfy all these rules, and the definition of the average. Since now if you average this, of course, average of small u is 0, as it should be. That's how you define the average. Small b average is 0. Now suppose you take the induction equation and carry out this process. Start with the induction equation. Okay. Oh, I should write the induction equation. So you have dB by dt. Imagine that all these have vector signs. U cross B minus eta curl B. Now I stick in u equal to u bar plus u and b equal to b bar plus b. So you have dB bar by dt plus d small b by dt. There are 4 terms here, u bar cross b bar plus u bar cross b plus, what is that? Small u cross b bar. Can you see here? I'll write here, small u cross b. And there are 2 terms here. So this is the full, I have not done anything at present. Then you average this. Okay? So average will kill this term because its average is 0. Average will kill this term because this average is 0. Will kill this term because its average is 0. It will not necessarily kill this term because these are 2 fluctuating quantities. Individually their averages may be 0, but the product average need not be 0. So then you will get what I have called that the mean field equation, curl of u bar cross b bar plus u cross b average minus eta 12 of b bar. Okay. This is the equation I have written down. That small u cross b average is called the electromotive force. Okay. Somebody called it that first time. You can also write down an equation for small b, because you just take this equation, the original equation, and subtract. And that will give you an equation for small b. That of course has this nonlinear term, because you had this u cross b in the original equation. You subtract average u cross b, that will still remain. Okay. The whole headache of doing mean field dynamo theory in this way is, how do you find this electromotive force u cross b average and express it back in terms of the mean magnetic field that you have? And that is a closure problem. It's a closure problem even if there is no Lorentz force. Basically because there is the small u cross b. Okay. Now what do? People do then the simplest possible thing. The simplest possible thing is to drop things which you don't like. Okay. And so suppose you drop that nonlinear term. Okay. Oh, here I have even gone further. In fact, to find this, there are different ways of doing this. One is the traditional way of just trying to solve for small b. Okay. The idea is that this equation, you could imagine that you can express this electromotive force as something proportional to b bar itself, something proportional to curl b bar. In fact, you can write down a whole bunch of terms which are all proportional to the field itself and its derivatives, because it need not be isotropic. It can depend upon some indices can be here. Okay. Now, if you manage to do this you can only do in some two limits. One is if there is a large, if there is a very small magnetic Reynolds number, then you can say fluctuations are small, and then you can solve this equation better. The other is usually when the correlation time is very small, but we have just seen that when regardless of correlation time, if you have lots of Reynolds number is large, you will get a growing fluctuating field through the small scale dynamo. Nobody knows how to do mean field theory in the presence of strongly growing fluctuations. Maybe a strong statement, but because usually one does mean field theory when fluctuations are small for some reason or the other. But if you have exponentially growing fluctuations, then the mathematics of trying to do mean field theory is shaky. But let's proceed and see what happens. So one way of doing it is the traditional way. You say that the EMF is basically u cross b average. You substitute for b the integral of dB by dt over time. The argument being that suppose you are given this u, suppose you are given this small u, okay. This equation is basically linear in b bar, okay, and you should be able to establish everything. You are given this u, you only need to know what b does, small b does, and so you plug this in. Then you have to pick up terms from the small scale field, okay, which is here, this one. The most important term which depends on b bar is just the induction effect of b bar by the small u. Okay. Now you use that, substitute for that term, and you get two such terms. One is an advection, one is a stretching term. This one, you assume isotropy for the velocity field, and you will be able to show that the one which depends on the gradient of the velocity will give you a part of this turbulent EMF, this alpha, which depends on the helicity of the turbulence. The one which doesn't depend upon the gradient of the velocity, which is the advective term, will give you something which adds to the diffusivity of the mean field, called the turbulent diffusion. Now physically this is actually quite interesting to ask. If you had, for example, I think Chris showed this nice example of a die, and you have turbulence. Somebody created turbulence and it all nicely mixed, and it mixed on a very rapid time scale. Okay, it mixed because there was something called turbulent diffusion. Usually diffusion of, let's say, a particle will occur because of random Brownian motion. That Brownian motion will involve small steps corresponding to the mean free path of the particle, like the air in this room. Okay? If you have just got some dye or some smoke or something in one corner of the room, you can actually calculate it will take a few days to go to the other corner. But turbulence enhances this, and it enhances this from the very simple fact that the mean free path is no longer the relevant scale. The fluid moves on much bigger scale and advects the particle of smoke. So now no longer the random walk is random walk of the particle itself, but the particle is strapped to some lump of fluid, and that fluid itself is moving around with very big steps. So it can move randomly from one end to the other on a much shorter time scale. And that's exactly what happened in that movie that Chris showed you, that you started with some dye and you stirred it, and very rapidly it kind of mixed. So that is turbulent diffusion. It's very easy to imagine physically. The magnetic field has a more interesting feature. Whereas you cannot generate smoke by just stirring, you can generate magnetic fields by shear. So a vector field frozen into the flow is very different from a scalar field like smoke frozen into the flow. When a vector field is frozen into the flow, there are extra shearing effects and the field can get amplified. This is exactly the thing which amplified the field in the fluctuation dynamo. But in the presence of helicity, that term, which is the shearing term, p bar dot grad u, which when you cross with u, is exactly the term which goes to determine this something called the alpha effect, which depends on helicity. So once you have helicity in the problem, the mean field equation becomes, okay, I won't go into that thing, becomes something very different. This electromotive force, E, which was U cross B, has a term which is turbulent diffusion, which just adds to this eta and sits there, which was a normal diffusion like smoke kind of thing. But it also has a term which, if helicity is present, depends directly on the mean field itself. Okay? What does this term do? It can grow the field. So you can get growth of the mean field in the presence of helicity. Okay? And coming basically because in the presence of the helicity, the shearing term organizes itself to grow the field. Of course, I'll also show some pictures. So the way, for example, the large scale field is thought to be generated in the galaxy, and this equation is also used, for example, in all other mean field type models of, let's say, the sun, or I don't know whether Earth, probably, I don't know whether you have such a mean field dynamo equation. No longer, I guess.
No longer really.
Because you're doing direct simulation of everything, right? So this is something which is being used, for example, in the galactic context to understand the fact that you have coherent scales much larger than the scale of the stirring. Okay? So the two things which go on is, firstly, there is galactic shear, which generates some field. And why is there a galactic shear? I said I will show this later. The galaxy has a rotation, and this is the rotation velocity as a function of distance from the center of the galaxy for various spiral galaxies which have been plotted. And you can see the rotation velocity kind of goes to a constant at large distances. This is very important from the point of view of dark matter, which is not my topic today, okay? Because that shows that there is more mass in the system than what you can infer from the disk light profile. But what is important in our context, if velocity goes to a constant, omega goes as 1 over r, so d omega by dr is not 0. So there is shearing in the system. What does that shear do? If you have a radial field going into the galaxy, let's say, and the center of the galaxy is rotating at a faster angular frequency compared to the edge, it winds up the field. This is exactly what you were asking that this will do always in a galaxy if it's frozen. But the growth of the field will only be linear in time. So suppose you want to produce microgauss fields, and you want to start from a seed field, you have, let's say, 30 rotations of our galaxy over the age of the galaxy, let's say. Then it will grow by a factor of 30. But of course, it will also do a different thing. Whenever you have shearing motions which are growing something, you know it's coming from flux freezing. Whenever you have flux freezing, you are always paying a cost. You are always squeezing the field somewhere. When you are stretching it somewhere, you are also squeezing it in the perpendicular direction, and that's how you are growing the field. So if you have lots of random fields, it also produces large number of reversals of the radial along the radius, and that you don't infer from observations. So this shearing will not just do. It will grow things linearly, it will produce lots of reversals. So what does help is this extra bit, the alpha here. If you put that term in, then you can find that you can get exponentially growing solutions instead of linearly growing solutions. And you can also see why, because suppose you take the same toroidal field which is here, which is being sheared by the galaxy, let's say, and you ask what do helical motions do to such a field, okay? Because they are alpha dependent upon the helicity. Then a little parcel of gas will be picked up and will be twisted by helical motions, okay? For example, here these are pictures drawn by my friend Anwar. He's very good at drawing pictures, and these pictures he drew for his book, and he drew it when there was no fantastic amount of software available. I think he drew it by hand. So you can see the quality of the pictures that he can draw. So you have a little parcel of gas which is being lifted up here and then twisted, okay? So when you lift up the parcel of gas from this B5, you produce a little loop here. That little loop will correspond to a current which is going through that loop. When you twist it, you produce a component of the current parallel to the original field itself, or in this particular case, anti-parallel to the original field. Now you may imagine that if you have random motions, you will cancel out such a current. But if you have net helicity in the flow, when you go up and you twist in one way, you produce a current in some direction. When you go down, you twist the opposite way because you have helicity. And you can think about it, you will produce the component of the current parallel to the original field will be the same. The one which is perpendicular to the field will cancel out. So you can draw these simple pictures and convince yourself that helical motions will produce a current parallel to the original field itself. A current parallel to the original field corresponds to fields in these directions, in R directions and phi Z directions. So that will produce a radial field, which can now be sheared to produce a toroidal field. So I've probably given you 3 different ways of looking at it. You can look at the Kazantsev problem and say helicity opens up a bound state to a tunneling state. I've given you the simulation which just shows you whatever. The mean field theory, which shows you there's an alpha effect which comes from the fact that whenever you have helicity, the stretching term in the induction equation leads to an extra electric field parallel to the original field, which allows for exponentially growing solution. Then I've given you a picture which says that from radial fields you will produce toroidal fields, and from toroidal fields, if you have helicity, you will produce radial fields. Of course, if I've given you 4 different ways of saying something, there must be something wrong with it, right? In the sense that, okay, all of them are right, but why am I saying it in these so many different ways? Apart from aiding understanding, it's a very complicated subject because you have high Reynolds number, you have closure somewhere, you have turbulence somewhere, you have small scale fields, you have large scale fields. So it's a picture at present, and it's kind of working hypothesis that people take that this is how the galactic dynamo works. And some people try to explore further the consequences of this for observations. You can also ask what are the problems with the picture that I presented. And I think in the last half an hour, I'll look at the problems more than the consequences. There are 2 interesting problems straight away. One is to do with what is now called magnetic helicity. Now, magnetic helicity, I'll come back to this picture, is defined usually as an integral over A dot B. A is the vector potential, curl of A is B, okay? and V is, the volume is supposed to be a closed volume in the sense that no field penetrates this volume. Either the volume is at infinity so that the field dies, or the volume is some finite place where the field kind of turns around. There is no normal component of the field. Why? Because vector potential is not a gauge invariant quantity. You can always add a gradient to the vector potential and keep the same magnetic field. So if this thing, if it has to be gauge invariant, okay, if I add a gradient to the vector potential, that extra term has to go to 0. Okay. That can only happen if, so suppose I define an A dash, which is A plus grad lambda here. So A dot B will become A dash dot B dash will become A dot B. Then the gradient term will involve this term, right? And that will become divergence of B lambda, which will be a boundary term. So only if the field at the boundary vanishes or goes to 0 will this definition of helicity be gauge invariant. And you don't want to deal with things which are not gauge invariant. So usually this is the definition that you'll have. The physical meaning of helicity is also interesting. Suppose you have two loops of flux which are linked like this, and you ask what is the helicity of that. You split up A dot B dV into A dot dl and B ds. B ds is like the flux. Okay? So this A dot B will only be important where B is non-zero. So it will be only along this flux tube. Along this flux tube, you can split up the volume as a ds which is perpendicular to the tube and a dl which is parallel to the tube. So you write A dot B as the flux, which is phi 1, times A dot dl along this curve, phi 2, which is this flux, times A dot dl along this curve, C2. Now look at this. This integral will become curl of A dot ds by Stokes' theorem. That ds will be the cross section of this loop here. Not this cross section, but this area here, enclosed by this circle. That will only be non-zero if the other flux is penetrating through that. If these two loops are unlinked, that will be 0, because that will be B dot ds through this area here, which is contributed by this flux loop. Okay. Similarly, for this flux loop, A dot dl through C2 will only be non-zero if this loop is penetrating here. So only for interlinked loops you will have non-zero helicity. If the loops are separated, then you have zero helicity. So helicity basically measures the topological property of links in the field. It also measures twists, but twists you can look at as interlinks. Suppose you take a flux loop and twist it. Okay? You can take a central field line and take other field lines as linked to this central field line. So basically it measures this topological property of linkedness of these fields. Now let's go back. Okay, before going back, let's go forward. By the way, this is IUCAA's symbol, and you try to calculate the helicity of this and it turns out to be 0. So not all topological properties of the field are described by magnetic helicity. I always say this, that okay, in any place like IUCAA, there are lots of positive links and negative links, and they all cancel to 0. In any institution, in any... Yeah. You are questioning that?
No, I'm not questioning that at all. I'm just saying, how will this relate to not
Oh, that's a big thing. I never found a discussion. I never found a good discussion of the more complicated knots and how they relate. It's an open question, I think, and I'm going to come to something important about the helicity. So you can ask, how does helicity evolve with time? Okay. So it's very simple. You just uncurl the Faraday's law. You don't even need induction equation. You uncurl Faraday's law. You say B by dt was curl of E. So dA by dt, when I uncurl that, will become E plus some gradient of phi, because you can't throw that away. Curl of this will be Faraday's law. So d by dt of A dot B, you have two terms. One is A dot dB by dt, which is written here. One is dA by dt dot B, which is written here. This obviously contributes an E dot B. This obviously can be written as divergence of phi B, because divergence of B itself is 0. This one you can shift the curl to the A by integrating by parts, and that will contribute one more E dot B and leave a divergence of A cross E. Now, this term is a volume generation term for helicity density, but I have to integrate this over everything, right? Now, suppose I stick in Ohm's law here, that the electric field is U cross B plus J, okay? Then U cross B dot B is 0. So, any velocity field which is doing induction will not change the helicity. So, it's a very strong statement, will not give you volume generation of helicity. The only thing which will remain is fluxes of helicity, okay, because of this divergence term, and the only volume generation term which remains is the resistive term, eta J dot B. So, suppose you have a system where all you are integrating over infinity, or you have closed fields so that there are no fluxes of helicity out of the system, then helicity evolution is governed by J dot B. I have not derived this equation, nobody has derived this equation. The energy evolution is governed by J squared. And of course, the work done by Lorentz force will transfer energy between velocity field and magnetic field. This is the Lorentz force, and V dot Lorentz force will transfer energy. In the induction equation, it will come with one sign for magnetic energy. For the kinetic energy, it will come with opposite sign, so that you get energy transfer between the two. Now, a great thing happens. Suppose you look at the loss of helicity. However small the resistivity you take, the loss of energy will always go to a finite value. This is something which Alex also mentioned, that if you have very small resistivity, you will develop gradients so that current sheets develop. In those gradients, the energy will be magnetic energy will be dissipated, and you lose the magnetic energy as fast as you put it in somewhere. They will always go to, however small you make the resistivity, the magnetic energy dissipation always goes to a finite amount. But the helicity dissipation can go to 0. Because there is a B here, even if the current is confined to very narrow regions, the magnetic field is not, because the curl of the magnetic field is the current. So if am I saying it right? The curl of the magnetic field is the current. So if I want the magnetic field for a given current, I have to uncurl. Uncurl is a global operation, not a local operation. Another way of looking at it, if I have a wire carrying a current, the magnetic field is not just in the wire, it's all over the place, all over the regions. So even if the current has some small scale, the field does not have the same small scale. So if I take eta going to 0 and roughly say that to make this finite, I have to scale J as 1 over eta to the half and B as eta to the 0, dEb by dt can go to a constant, but dH by dt can go to 0, because 1 eta remains here. So a very interesting result is that in not an ideal, but very good conducting plasma, helicity is a better conserved invariant than the energy. So if it's an ideal plasma, everything is, sorry? Even total energy is not conserved, because viscosity is also there for the velocity field.
Yeah, so will the helicity be finite at u going to 0? Do we know that?
Sorry?
Is the dissipation of helicity going to be finite
Yeah,
when the eta goes to 0? Do we know that?
yeah. This is, no, it doesn't, it is not going to be finite, it's going to 0.
It's going to be
0, yeah.
This is definite.
You can always construct examples. You can always construct counter examples where the helicity will be dissipated as fast as the energy. Suppose you take just a current loop which is helical. The field is all confined inside that, and you have it on the resistive scale. Everything will disappear together. But in many contexts, and for example, in some turbulent spectral kind of arguments, you can find that the helicity is a more rugged invariant That is, both are invariants in the ideal case. If viscosity is 0, resistivity is 0, there are 3 MHD invariants. The helicity is 1, total energy is the second, because these Lorentz force term will cancel between the kinetic and the magnetic, and the cross helicity is the third invariant. These are the 3 invariants for ideal MHD. If I now make it non-ideal and make small resistivity, small viscosity, you can ask which is a more rugged invariant, and it turns out helicity is a more rugged invariant. It dissipates slower than energy. In fact, we even see it in some of the simulation which Pallavi has done, and I may come to if I have time later. And in fact, that is at the root of what in the plasma physics community people call Taylor relaxation. You have some helicity in some experiment which you inject, you have some random field, you allow it all reconnect, dissipate, but you cannot go to zero field state. You go to a very ordered state called the Taylor state, which conserves helicity but dissipates energy. Okay? Now, if this is true, if helicity is nearly conserved, and I had these nice pictures, you have now formed links of the mean field. So if you have formed these links of the mean field, you have got some mean helicity, but you started from weak fields, no helicity. So how did the helicity in galaxies come about? So this is one question which has driven a lot of work in the last decade or so. The other question, which I'll just mention now itself, is that we saw that you require only a modest magnetic Reynolds number to have this fluctuation dynamo growing fields very rapidly. And I've been saying all these mean field closures and all that. So in the presence of these rapidly growing fluctuations, it will saturate at some stage. It will grow such large amount that your Lorentz force will become important. Can the mean field still grow? Usually, canonically, it's supposed to grow slower than the fluctuations, because fluctuations are growing on the eddy turnover time scale. The mean field is growing on the time scale, which I've given here, on some rotation time scale of the galaxy. So will saturating that fluctuation dynamo saturate the mean field dynamo? That's the other question. So in the 20 minutes that I have, I think, let me try to say something about both of them. First, about helicity conservation. These are 2 flux tubes made at home by Anwar and his wife, Natasha. The flux tubes were actually hose pipes. They took their hose pipe in the garden, and they painted one, a lot of hard work, right? And especially to make your wife also do. So they painted one of them black, one of them white, and they wanted to look at helicity conservation. So this has been kept like this, and then it has been writhed. That's what we are doing in the alpha effect. We are lifting a bunch of field lines and twisting it, writhing it. That's called a writhe. So when you do that, for example, what they've showed in this experiment is when you turn this tube itself by 90 degrees, okay, you can see the black and white have interchanged. So you conserve helicity, because this rubber is like flux tube, rubber hose pipe is like that. You can't break links and all that. Okay. When you writhe it in some way, you also produce an internal twist such that the same 90 degrees twist has been applied. So you conserve helicity. Helicity doesn't get broken in this ideal limit, helicity conservation. But there is one sign of helicity on the scale of the mean field. There must be an opposite sign of helicity on the small scale field, which you are not seeing, and you have thrown it under the rug. Okay. Similarly here, for example, they have turned it by 180 degrees from the straight, this thing like that, and then you see everything is reversed. Black has become white at the other end. So it has got the 180 degree twist. Now, if you imagine the same thing happening, you could imagine that it's very difficult to twist hosepipe comparing to writhing it, because the scales involved are different. When you writhe it, you are doing something on this big scale. When you're twisting it, you're doing something on the small scale. And you can imagine that if you conserve helicity and do this, the forces may not be the same because the scales are different. Although you have conserved something, this is the helicity, the Lorentz force due to the twist is much bigger than the Lorentz force due to the rise. And you can show this explicitly because the force involves J and B. Helicity involves A and B. So there are two Ks extra in the force. If you take J as curl of B and B as curl of A, there are two wave numbers extra in the force. All cross product, dot product, all with notwithstanding, right? So in principle, the Lorentz force will grow faster, even though you are conserving helicity on the small scales. On the large scale, suppose you are conserving helicity, the Lorentz force on small scales will grow faster. That will come and back react first and stop your writhing. So the quenching of that alpha effect, the helicity, could come from just the helicity conservation, which puts opposite sign twists in small scales, and that will maybe quench things much before you have had the field growing significantly. This is one problem. I have put all that in these pictures. You can do it mathematically. You can ask what is the helicity conservation equation for the mean field, and you had E dot B that you replaced by the E bar, the mean electric field, which also involves this turbulent electromotive force, because it's not just U bar cross B bar, but also small u cross small b average. U bar cross B bar is perpendicular to B bar, so that goes to 0. But the electromotive force which involves this has a component parallel to itself also. So that comes and sits here. You subtract this from the total helicity equation, you will find the equation for the small scale helicity. And you can see, and this is by construction, that there is a plus sign here and negative sign here. They have different dissipative terms, but basically the electromotive force which is involved in the dynamo generation process is transferring helicity from big scale to small scale. So now it's transferring between scales. Now this potentially has a problem. So suppose you